Okay, welcome back. So yeah, welcome back to the end of week 3. And today we are going to wrap up on the subject of electrostatics. Basically, we have introduced all the key ideas in the past 2 lectures already. And now we're going to just marinate in them a little bit more and get a better understanding of them. So we have the motivation down. We know why are we interested in them in the first place. We're going to dig a little deeper today. And also we know some basic formulas, and we're going to explore them a little bit more today as well. So as common is, as you already probably see from today's discussion session, electrostatics is it's one of the subjects where actually even going forward in the next, the remaining 2 weeks of this course, a lot of these ideas will be very different in terms of problem solving skills and the concepts. So although the discussion sessions are optional, but I think you'll be basically learning completely different things. So you'll be learning the actual problem solving skills. So in some sense, if you like to think of it this way, the lectures would be, sorry, I don't know if Zoom is reacting well. Am I still here? Just checking. It just froze a little for me. Okay, good. All right, thanks. So yeah, thanks for helping me check every now and then in case something goes wrong. What was I saying? Right, so yeah, in some sense you can think of the lectures as helping you with the short answer question segment, the first 5 points in the test, right, out of the 10 points, and then the discussion session and the homeworks will help you with the second 5 points, the open response questions of the test. So you can think of it in some sense that way. So I think this way of doing the test, it tests you a balance of putting you so that the focus is not purely in the plug and chuck regime of things. And even in the open response question, I hope one thing I am encouraging you to see in physics is the plug and chuck bit is really just 20% of the problem, and 80% should be analyzing the problem until you set it up correctly. That is maybe 2 out of 5 points. So that's 40% of any physics problem. And then the next 40% is using your logic to make arguments on how to simplify the steps, how do you draw in different concepts, and then at the final step you plug in the numbers, so that counts for like 20%. So yeah, so that is sort of the goal. And also, if you don't know already, the 3 discussion sessions, because we have 3 TAs, so what I decide to, instead of everyone doing the same problem, I give a variety of problems. So some of you have tackled the electric forces and fields, some of you tackled the electric potential, and some of you tackled potential energy. And I'll encourage the TAs to upload their recording as well, and you can use those as extra resources and look at other discussion classes, so you can see how different TAs solve different things as well. Okay. Yeah, so that hopefully gives you a lot of variety of explanations from different people. We also got new LAs. Hope you have had a good time meeting them, and hope they're a great addition to the class. Yeah, all right, so today we're going to cover a couple of things. In fact, let me start with the opening question for today, since it's always good to know why we're doing something, right? And today, by the end of today, we should be able to answer a another pretty deep question. I know I've been overusing this word a lot, but I'll let you decide. Today, the question we can answer is finally, why do like charges repel and why do opposite charges attract? I stated from the very first lecture of this segment of electrostatics that this is a fact. But how does that do that? And in some sense, that would lead us to the question of how do non-contact forces work? I don't know if you've questioned that yourself before, or you're just told and you accepted it without thinking. But if you think a little bit more about it, when someone tells you, oh, gravity acts from one place to another, how does it do that? Right? It's not, if it's something that's in contact, we kind of understand that, although at the end of last lecture, I made the point that the fundamental forces are important because even contact force is non-contact force. It's really just 99% of almost every contact force you can think of, it's due to electrostatic force. It's actually electricity. It's actually electric forces, the repulsion between electrons on your surface of your hand and the object of interest, right? But nevertheless, if we zoom out, it kind of makes sense. I push something, that exerts a force. But if I don't push on something, if I don't touch something, let's zoom out, forget about the microscopic side. How does one thing act on another? I'm not going to write this in full-length sentence, but I'll just say, you know, you have two positive charge. How does this, why does this happen? Or if it's positive and negative, why do they attract? And like I say, this leads us to an even deeper question of actually, how do these non-contact forces work? Okay. And we'll have an answer. We already have the answer, but we'll be able to phrase this in a more complete sense at the end of today and wrap all the concepts up. And then to give you an orientation as well, next week, we'll look at circuitries, all the electric circuits, and we'll see how these ideas, it's a little bit of a drier topic. If you, I know what some of you may be thinking on electrostatics, because we're introducing these very abstract concepts, but we'll see how this is forming the basis, the basic physics of making circuits work. And today at the end, I'll throw a few applications as well. Okay. So we'll cover a few things today. So so in past two lectures, we've introduced, especially the last lecture, we've introduced a few different concepts: electric potential energy, electric potential, and then electric potential energy difference, and electric potential difference. Okay, I'm gonna get tired of myself saying electric over and over again, since we're not, most of the time, we're not talking about gravity. These are the only two non-contact forces we know so far. I'm gonna drop the word electric, right? So I'm just gonna talk about potential energy, potential energy difference, potential, and potential difference, okay? And so we have these four. The first thing we'll address today is provide a unified link between them. How does this relate to each other? How does this relate to this? How does this relate to this? And how does this relate to this? Okay, I'll do it in the order of, I'll start with this, and then I will start, and then we'll look at what's the relationship between potential and potential difference. Should be rather simple. And what potential difference, energy difference, and potential energy and potential energy difference. And then how about between potential and potential energy. And then once you understand, the last bit is very straightforward. You know, that's just a change of them. All right, so that's the first thing we'll address. This part will be a little bit more mathematical, maybe a little bit less relatable in some sense until we see applications. So I promise I'll show you how these manifest into applications at the end. In fact, we'll see how a television set works at the end of today. And so that's number one. And then we will talk about equipotential surfaces. This is almost like the analogy of electric field lines. It's a way to visualize. So it's a way to visualize potential, okay? Where just like electric field lines, it's a way to visualize electric fields, right? So that's one thing. And we'll look at some applications. And I'll make some comments, especially about conductors. Okay. All right, so that's the plan. Now, let's actually start with answering this opening question over here. Okay, so I'm going to rephrase that a little bit. Instead of why things repel, I'm going to rephrase it into why things move. Okay, so I'm going to rephrase it into why do things, in fact, electrical things, more specifically, let's talk about electric charge, right? We're looking at a subset of things that have electric charges. Why do these move, right? So this is essentially, why do the positive charges repel each other, right? Okay, so there's two answers. Okay, answer number one, as we mentioned, is the force perspective. Okay. The force, so this time, this is the picture. Although I have two, although I have two charges, first, in physics, we want to keep things simple. Remember, the mantra of physics is to make things as simple as possible. Even though in the beginning of the course you may not agree, but hopefully you start to see the philosophy of how physicists think. Things are complicated. Even two things is too complicated for us. Let's reduce that to one thing. Let's just analyze why does, let's say, this guy move. I don't care about this guy, all right? So now I've differentiated it. I would say this guy is the source and this guy is my object of interest, which we'll call a test charge, okay? So the source, I don't care what it does. Assume that's not moving. Let's say you take a nail and nail it down on the table. So I'm just asking, all right, we know this guy will feel a force from this guy and then we'll move to the right. It'll get repelled away from the source, right? But how? They're not even in contact. This is the answer. The source is going to emit an electric field, okay, right? So the source is, as we learned, the source emits an electric field and the test charge happens to sit inside the electric field of the source. And as a result, the electric field is causing this guy to move. All right, so it's a two-step process. I'll write it down, summarize it in a second, but let me repeat my words first. First, the source creates an electric field and the field, so it creates an electric field in its surrounding space, okay? And then this guy, the test charge, your object that you're actually interested in, happens to sit inside that field, so it experiences, it feels that field, and that field is what's causing it to move. Now, the field is a very abstract concept, but if you invent this concept, now you have an answer of why this move without touching. This guy does not need to touch it because this guy emits a field, and it's a field that is causing this to move. I know it almost like I didn't really answer it. I've replaced one unknown word with another word, but this makes a more powerful analysis because not only, if you have a deep question in life and then you ask the question and someone gives you an answer in terms of another word that you don't understand, your life is not really better off. You're just replacing one mystery with another mystery. But your life is better off if the other mystery can solve more mysteries than the first one, right? So if you have a long list of things, you have to take it for granted, that's not very economical. However, if you can replace it with one mystery, but if you accept this mystery and everything else can be explained from this, now it's a much more economical way of thinking and much more powerful way of thinking. So that's the idea. So we step back and become more abstract, except things will emit electric fields. And then not only will it answer why this moves, it will answer other things. For example, ultimately in 3C, one of the end goals in 3C, the very, very ultimate end goal is you'll see how light works. What is light? And light is basically entanglement of electric fields and magnetic fields. So without the concept of electric fields, if you just say, just memorize, positive charge repel, opposite charge attract. Good, I've just memorized that fact. Why do I need to memorize another fact to explain this if this is not? The point is, this actually explains much more physics than if you just do this. If you just have this, you will not be able to answer what is light, okay? Right, so I won't write in full sentence, but just to give you an idea, right? So the source emits a field. Okay, I'm gonna drop the word electric, right? Remember, because everything's gonna be electric. So the source emits a field, and then the field creates a force on the test charge. Okay, so in equations, how does that work? Right? So first your source creates this field, right? So this is the electric field of the source. In fact, this is the formula. Don't get it mixed up. This is not in general true. The general definition is force per unit charge, but for a point source, I should put that on top. Yeah, you get the idea. For point source, you have this formula. So the charge of the source creates a field, and then the field, right, creates a force on the test charge. So now, so this is the logic, right? So this creates this, and then this exerts a force on this. So this guy experiences a force to the right, an electric force to the right. Where does this force come from? It's because this test charge is in contact with the field. It's not in contact with the source, so it's not a contact force per se. It's in contact with this imaginary object called a field. Okay, so hopefully with the 3 lectures in, there's no way to make this easy to understand. It's really just repetition and getting more and more used to it. So hopefully from 3 days in now, you feel a little bit more comfortable than the first day you heard about this idea. So that's the goal, right? Once you have the force, you see you can use Newton's second law, right, on the test charge. Now you can calculate the acceleration of the test charge, and then you go and integrate this all the way, and you find out finally the ultimate holy grail of the x of t of the final how this test charge will move. That so step 1, step 2, step 3, step 4. So this is how the source affects any charge that moves. Okay. Comment number 1. You might ask, does the test, well, wouldn't the test charge also emit an electric field and affect the source? Yes. This says force electric force. Scroll down. I don't think that's possible. I can zoom in. Does the test charge emit a field? That's the first question, because I said the source emits a field. Yes, the test charge does emit a field, so I can draw this field, but first of all, it will make my diagram very complicated. And secondly, if the test charge emits a field, what it's going to do, I just need to mirror the whole logic. It will make this guy move to the left, right? It'll make the source move. But I'm not interested in that guy. I'm interested in one thing at a time. I'm just interested in why this guy moves away from the source. I'm not interested in why the source moves away from the test. Another way of thinking is, for now, let's just keep it simple. Let's nail this down. So this is not moving. Sure, it'll experience a field. As long as the field is weak enough, it doesn't break my nail. This will just stay where it is. It's not going anywhere. Yeah, anyway, yeah. So the key is I'm interested in this first. Okay? So that's answer number 1, okay? Sometimes people say, use the words saying that the test charge sits in the field. It sits in the E field of the source, right? So the source creates a field and then it's experiencing that field. Now, today yesterday we realized that there's a different answer to the question. There is the energy approach. So there's the energy perspective of things. Okay. And there should be benefits and there should be pros and cons for each one. Okay, so how does this logic work? This is what we'll explore a little bit more in depth today. So I'll give you a brief, quick answer first. So this time, forget about remember how we should treat this when we study when we study the energy approach. You should forget everything in the force approach. So forget about fields, okay? Even though I spent the past 10 minutes talking about fields, now forget everything about it. And imagine this guy, the source, it's emitting something called a potential around it, okay? Like a potential field. That's not a right. By field, I just mean in the layman sense, not the technical electric field sense. Right? There's a land of potential. Like there's a field of potential, and these are going to, as we'll show in a second, represented by equipotential lines. So on each of these dotted lines, the potential is going to be the same. We'll explore that in a second. Here's just a brief motivation like that. Okay, so the source is emitting this. Again, yes, the test charge does emit one as well, but I'm focusing more on the source at the moment. And this time the test charge doesn't sit in the field of it. Remember, we were forgetting everything about fields. This test charge is sitting in the potential land, right? The field of potential, right? The land of potential of the source. So the source emits a potential, and this guy sits in it. And this guy, the potential does not make it move, but its potential difference that will make it move, right? So the chain of logic is this. The source emits a potential using this formula, right? It's a point source, so I can use the point source formula. I made a mistake yesterday. I wrote the minus sign here. I'll address that later on. Okay, so that's the formula for a point source. So the source will create a V, a potential, and then the potential would, and then it's the potential difference, okay? It's the fact that here, this potential here is at a higher potential than the green line, okay? So the blue line will have a higher value, let's say 90, and the green line has a lower value. And we will learn that positive charges will always go from high potential values to low potential values. It's almost like rolling down a hill. It goes from high heights to low heights. It'll go from high potential to low potential, all right? So the potential difference, as we'll see, will create a potential energy difference. So it'll create a difference in electric potential energy on the test charge, okay? Again, the difference is going to be important. How does that work? It's because it's related by Q times delta V, right? Delta U is Q times delta V. So any difference in V will create a difference in U, okay? And now how does that cause anything? So a difference in EPE, in electric potential energy, will create a difference in kinetic energy, right? Because remember, energy is conserved. So any change, total energy, right? So change in potential energy plus change in kinetic energy should equals to 0. So if you have any, if you put that to the other side, if you have any potential difference, it will create a kinetic energy difference. So it will make things move. If it starts off 0, it will not end up at 0 velocity. It will start to move, right? So source create potential and a potential field. When this potential difference, it will create a potential energy difference. Potential energy difference will affect kinetic energy. So it'll make this move, okay? So that's the perspective. We'll explore these a little bit deeper. So this we have answered basically how does non-contact force work. If you rewind for in the past 6 minutes and replace every word I say with from electric to gravitational, gravitational field, gravitational potential energy, kinetic energy, it's the same theory. So the non-contact force of gravity is this exact same idea. So it's also you need to replace the word charge with mass, because that's the gravitational charge. Mass is what gravity reacts on, right? Those are the actors of gravity, the force of gravity. So the one mass over here, there's a source mass, like the Earth would create a gravitational field around like apples and people like you and me. We are sitting in the gravitational field of the Earth, which is G 9.81, and we feel the force, right? That's one way to think about it. So that's another way is, for example, this is the Earth, this is the Moon. It can be an Earth and an apple. It doesn't matter. It's the same theory. The Earth has a gravitational potential surrounding it. That's the energy perspective. It's emitting that, exuding, this potential around it. And the Moon would be around here, and it will try to move from. It will be attractive, not repulsive. It will go this way or something like that. So this is how non-contact forces work. It's going through a medium, either with the field perspective or the potential perspective, force perspective or the energy perspective. Okay. All right, so now the next question you might have is, why learn something new, right? That's perfectly good with fields. We know how free body diagram works. We can just add up these things. The answer is really, it makes life a lot easier. Even though potential is more abstract, it makes things easier, okay? The punchline is because it's a scalar. Okay, just to elaborate that on a little bit more. So why need a new concept? Why need this very abstract thing called a potential? Well, the answer is, if I have multiple sources, let's look at this scenario. If I have multiple sources, right? If I have one that's positive, one that's negative, another that's positive, 1, 2, 3, let's call it. And I want to see, so all these are sources, and I am interested in this guy. I'm interested in the motion of this guy. Okay, so what is the net force this guy feels, right? Okay, so now we know, first you draw electric field lines from everything. So this guy does this guy does that. Locally it does that, but I'm not going to draw it all the lines extending out. I'll just draw the one that actually affects my test object. So this is the test. Okay. And for this, the negative one, there's this line that will, right, that is going this way, right? So technically, locally, there's more like this. And let me change the colors. So there's this one, this is positive, so positive field lines go out of, move away from the charge, right? Okay, so what is the, let's see if blue shows up well. What is the net force over here? Let's just use, yeah, I don't know if blue shows up well, probably not. Okay, let's use green. So the orange one, so due to the first source, due to the source number 1, it's going to create a force this way, right? And due to the source number 3, it's going to create a force this way. Let's use white, it's not showing up too well. And due to source number 2, it's going to create a force this way, right? So force due to 1 on the test, force due to 2 on the test. This is the force due to 2, and this is the force due to 3, right? So the F net, so previously, the way you do it is you look at F net, use the vector form and add up everything in vector form. Make sure you include the direction of it. So this is KQ1Q test over R1 test squared, right? And then you need to include the direction of that. Oops. This little R1 test is the unit vector. Zoom it in. It's the unit vector of the direction from 1 to test. So it's a small vector like this from 1 to test that tells me which direction it is, right? So this part is the magnitude, this part is the direction. Don't worry too much about this notation because we're not really going to use this R hat too much, but just showing you if you need to write it out formally, it will be like that. So 2 Q2 Q test R2 test squared and R2 test direction, and then the magnitude, and then 3 test direction like that, etc. But now you see that each term has a test, Q test over here. So in principle, you can factor out this and just have everything in terms of like Q1 R1T square, R1T hat plus all the other ones, right? And now you see everything in the square bracket, it's just due to the sources like Q1, Q2, Q3. It's nothing to do with the test. So this immediately tells us there's a more efficient way to do it. So it's with electric fields. Right? So that's why I say don't worry too much about this, because this is not efficient way to do it. You plug in, if I now change a different test charge, instead of looking at 1 coulomb, I want to know the force on 5 coulombs. You have to redo the whole thing. But with electric fields, it's much more efficient and more economical because you first calculate this, which is a pain, but it's the same pain. To do F1 plus F2 plus F3 vectors, it's the same amount of work to do E1 plus E2. So you just add the electric fields instead of electric forces in these directions. Once you have this though, it's much more efficient because now to find the F net, you just do Q test times E of the E net of all the sources, right? So once you find this, you can plug in any test charge you like. Okay, all right. So that is why we care about electric fields. Okay, but now I'm going to argue potential is even easier. Okay, so V is even easier. Okay, how would that look like? It will look like roughly like this, right? So each one will have a potential. So first, the first one will have a potential around it. All these, and think of it like an influence. Okay, so I'm only gonna draw the ones the ones that intersect my test charge. Otherwise, it's going to get a little bit out of hand. And so here, the negative one, again, will have a potential. And then the last positive one will have its potential over here. So now you add up. So the net V is you add up the orange one plus the pink one and the blue one. So V2, V3, V3, now you'll get the net potential, right? So we had the formula that's Q1 over R, I used small q over there, let me be consistent, over R1 test plus Q2 over R2 test. So this is the distance, R1, R1, R2, R3, right? To calculate actually these orange, pink, and blue values, these are the formulas for it. I'm not gonna make them the right color. If you are making pretty notes, you can make them the right color in each term, correspond to each potential term. Now look at this compared to when you do this or this. Here you have to resolve vectors. Here you just add up all the numbers. You plug in K, we know what it is. R is the distance, and Q is the charge of each of these. You just add this up. Look how much better this is. So hopefully I have convinced you that this is a more efficient way of doing things, even though it is abstract to learn. Does that make sense? Okay. So there's a question asking, do I know Q test? If you need to know its motion, yes, you'll need to know the Q test, and it will be given to you. Sometimes in the question, we just even forget about that stuff, and we just want to test if you know, we want to examine and test you if you just know how to calculate this. And sometimes we will go all the way and ask you how what is the final velocity of it, or what is the final force on the test charge. If you look at this formula here, you'll see, of course, the force, if your test charge is larger, the force on it will be larger, right? It's just like on Earth, if the gravitational force on an apple is smaller than the gravitational force on a truck, a ton of metal, right? But we all experience the same field. So this is, you can replace this with gravitational field, and gravitational force is the same idea, and mass over here, right? So the apple will experience a smaller force from the Earth, not because the field is smaller. We all experience the same gravitational field. It's just the test mass is smaller, right? So that's the idea. Okay, so here, the key benefit is, it's the best thing over here is no resolving vectors. Okay, so we all know how much you love resolving vectors, especially if you did a discussion session. One of the classes who did one on actually doing the resolving forces, you appreciated how happy that experience is. But once you learn potential, you don't need to do that anymore, other than the fact that we might test you to do that. But if you're a working physicist, you immediately opt to use. In fact, myself, when I need to do any of these calculations, if I can help it, I always use potential. So that now we have the right motivation to do that. So how does that move? So just how does that affect the test charge? The answer we'll see is, so you calculate, after you find out the potential everywhere, the potential is a feature of location. So it's just like the field, right? It's depends on the location and the source. So it depends on the location and the source. Oh, one more thing is, because it's a scalar, this time you don't plug in the magnitude of Q1, Q2, Q3. In here, you plug in the magnitude, because this part is the magnitude, this part is the direction, right? You can see that. So here, you always plug in actually the Oops, sorry. Oops. Sorry, guys. Are we back? Just checking. Okay, good. All right. I did refresh my computer and and using a landline and doing everything I can. So apologize for things I cannot control. Um, what I was saying is we put in the magnitude of the charges in here, but here you actually put in the positive and negative signs over here. So the potential of this guy will be positive because positive, 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 negative, positive, positive, positive. Okay, so that's one thing. Hopefully in the discussion session, you have addressed that practical issue over there. Okay, so the answer of how do things move is, so first you calculate the V of its surrounding around the test charge. So now, so what you need is you need delta V, and the delta V will tell you delta U by multiplying Q test. This is the change in electric potential energy. I don't know if you see that, but that's a change in electric potential energy, and that will cause a change in kinetic energy. So that's how the chain of logic works for the potential side of things. Okay. Okay. All right. So how does each of these relate together? It's what we want to look at. So the next few slides will be a little bit of more math just to tie all the equations together, but it'll be hopefully give you some better understanding of things. So first, let's start with the relationship between V and delta V. Okay. So V and delta V, how is it related? So V, if we want to emphasize it, when we say potential, usually we mean absolute potential. Okay, but I don't want to say absolute every time unless I'm emphasizing it. Okay, so if it's just V, it's potential. Just to recall, this is the work done per unit charge. So this is the main part, work done per unit charge. If you like, work done per unit test charge. So this is the main part, and then you need to know the fine prints as well to get the full points. To move it, it being the positive test charge from a reference point to R. So last time I said infinity to R because usually infinity is the right thing to use. But let me be a little bit more general today to be more general today first, that it can be any reference point. It also draws a little bit easier with gravity, the analogy. Okay, so that is in word definition, understand that. And also in equations, you have V of R is R naught to R, right? Because you're doing the work that brings this from a reference point to the actual location. So here I'm just being extra specific, specifying it in this location like that over Q test, right? Work done. So this is, you remember, this is work done per unit charge. In fact, let me make these subscripts, and these are important. It's from R naught to R, and this is R, like that. Okay. How about what's potential difference then? Okay. So potential difference, sometimes that will abbreviate it with PD, potential difference. You'll see that a lot, especially in the next chapter. For now, I might write pot diff, but later on, we'll just go to PD or just delta V if I want to use the symbol. So this is the same thing. It's the work done per unit test charge, almost everything, but not moving it from a reference point to infinity now. Sorry, not a reference point to R anymore. It's from one point to another. It's from point A to point B. Let's call it RA and RB. So it's the exact same thing, but it's moving from RA to RB. So how would it look in the equation form? So this time I will put AB. So technically I can write RA, RB, but you know what I mean. So just to make it a little bit easier. So RA, RB, and FDR. like that, per unit charge. So it's also work done per unit test charge, but it's not from the reference point anymore. It's just from the point A to point B, like that. So this is the definition for potential difference. This is the definition for absolute potential. Okay, got it? Okay. One confusing thing is the units for potential or potential difference, because this is just final minus initial in some sense, it's B minus A. The units is called volts. The SI unit is volts. So what's confusing is the symbol is also V. So you'll start to see equations like, oh, the potential at some point is 5 volts. So it looks like, do not cancel these out. Okay, so this is the unit. This is the quantity. It is confusing, but I don't know which genius came up with this idea. It is the way it is. All right. So let's see how these relate together. I can actually. So here's a little bit of mathematics. You can take the RA and RB, you can spread it out in 2 integrals. You can write it in from R naught to R naught to RB of FDR. The dot product here is important as well. So make sure you have a dot. Do not write 2 vectors together because this is dot product. The mathematics is important in that. We'll see an example later. Okay, plus RA to R naught of FDR. So what's going on here? Maybe I'll change the color of this and you can see a little bit clearer. I'm splitting the 2 integrals up like this. Before it was from RA to RB, like that. But now it's going first from RA to R naught plus R naught to RB. And I'm allowed to do that because there's a rule in mathematics, in calculus, that says integral of A to B plus integral of B to C is the same. If you are integrating the same thing, then it's the same as. If these are the same, then you just go from A to C. Right? So I'm reversing this logic where if you look at this side, right? So this is A to R naught and R naught to B, right? They can combine into just from A to B if they share a common factor like this. So this is just a rule in calculus. And now you see that another rule is I can flip these and change it to a minus sign. Okay, so there's another rule that says if I put a minus sign in front, it basically just swaps the top and bottom. So let's do that with the second term. Let's see what we get. So here we get R naught RB, same thing, nothing new. And here we get minus R naught RA F dot dr over Q test. And can you see now I have 2 potentials? Here, this is precisely the potential of RB. So this side is precise. Let's make it even a little bit more clearer. So I have R naught to RB of FDR Q test plus R naught to RA of FDR Q test, right? So this is VRB minus, sorry, that's a minus in between, VRA. And this is clearly as we expect. Right. So if I define it this way in my word equation, in my word definition, it's the work done per unit charge to move a charge from RA to RB. It basically is, that's why it's called potential difference, right? Because it's the final minus initial. It's just by the rule, these 2 rules of calculus that you can split this integral up, and then you can see it's the absolute potential of B minus the absolute potential of A. Does that make sense? Okay. So this is the relationship. So you can see that you can write the definition of this guy in terms of like this or like this. That's potential difference. This is potential. Now look at let's change everything to U and delta U. Should I even write it out? I'll write it out very quickly. It's almost the same thing. So the relationship between U and delta U, just so this time U is electric potential energy. Sometimes U is the best, most intuitive symbol, but we'll work with it. It's the work done not per unit charge. So the difference between potential and potential difference is this time it's just the work done to move a positive test charge from the reference point to R. Right? So this time it's almost the same thing. It's the potential energy at a point is you move from the reference point to R, but it's just the work done. You don't divide it by Q test. Okay. And very quickly, and if we look at the change in U, okay, so a change in potential, electric potential energy, or U, whatever you like to call it, so we'll call it delta U, is the work done to move a positive charge, blah, 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 to from A to B, from point RA to RB, like that, exactly the same. So from A to B is just from RA to RB. Okay. And I can do the exact same trick. First, I'll split it up into R naught plus R naught RA, and then I can flip the sign so that the RA goes on top and R naught goes on the bottom. Now, this one is basically U of RB. If you look at the first boxed equation on the top of this page, right? It's exactly this, and this is exactly this, right? So it's clearly difference. So, or I can just, now I can abbreviate it as UB minus UA like this if you want. So before you can also abbreviate that as VA minus VB. Yeah. So formally speaking, we should always write this. So it's a function of the position, but if we want to be quick, we can just abbreviate it like this if it's clear what it means. Okay, so again, as expected. Okay, so now remember that 4 corners. I have tied V with delta V, U with delta U. Now let's tie U with V. Okay, so let's tie the relationship between V and U. Okay. So the first two should be pretty simple. One is just a change, one is the absolute value, right? So what is it? U is, let's look at the word definition. This is work done to bring, again, I'm copying the same thing many times, but just to drill this in your head because you really need to know this definition. It's probably the most abstract definition of all the course, right? The whole course, by the way, the potential and potential difference for this. And it's the key word is work done, and then the fine print is to bring it from a reference point to R. Here, it's the work done per unit charge. Right, so this is the extra bit, and then it's the same thing to bring a positive charge from the reference point to there. So if you look at so this is in words, how about in the equation? One looks like this. So again, technically I should write this, right? So this R should correspond to this R. Yeah, I'll leave it here. And VR, V at a given location is FDR divide by Q test. So clearly the relationship is what? V is U over Q test, right? At that location, if you want to specify it a little bit more better. But the key bit is in white. Okay. So I remember someone on Piazza asked the question of what is, you find that confusing between V and U. This is the relationship. One is just divided by V. Okay, so this is the relationship, but if you rewrite it, just like a lot of things in physics and in life, I guess, if you rewrite it in a different way, you get some different insights. If you rewrite it this way, it's actually more practical. So if you like, you can put a star next to the second one. It is actually the more practical version. Why would I say this? Because usually the thing that we're most interested in to solve, we put it on the left-hand side, right? We use the right-hand side to solve what's on the left. And what do we care more about? Are we usually, if you remember the first few slides of what I'm trying to convey, is it what is our end game? Our end game is to get the potential energy difference. So we're trying to use V to find U, not use U to find V. Okay. I mean, in a test, in one of your homework, we can build an artificial example where I'll give you the U and find V. But in real life, in a practical situation, in real everyday physics, what we scientists do is we ultimately want to know how things move. So ultimately, we're trying to find V first and use V to find U. Right, so this is actually more practical, just like the force and the field equation there. And now, speaking of force and fields, let's recall what is that relationship. Remember, E in terms of word is force per unit charge. Right? So it's force per unit positive test charge technically, right? But the key word is the force exerted on a positive test charge, yeah, but the key word is force per unit charge. And then you remember the fine print is force on what? Force on a test charge, and it's a positive test charge. And the equation looks like this, right? It's E is F over Q test. So the definition of E is force per unit test charge, right? Remember that? So if I put a box around this, now you can see a parallel, or even better, let me rearrange it. Like I say, everything in life is better when you rearrange things this way. Can you see a parallel between the force approach and the energy approach, or the force perspective and the energy perspective, right? If not, let me draw the link. You should see, it looks like energy and force, energy plays the same role as force does in this equation, and field plays the same role as V does. Okay, so it is there is a very clear relationship in some sense. So V, this very abstract thing, is energy per charge. So V is probably the newer concept that you learn in this course. You probably know what energy is, and E is it's also a new concept, but force is the more old concept, right? So you take that and divide by the test charge, you will get this is the definition of the new concept. It's the whole idea of you're trying to find out something about the source. So you divide the effect of the object that you use to test it. Okay, so this is the relationship there. Thank you for your feedback. You're saying I'm going a little fast. Hopefully it's gonna be in the recording and you can revisit that. I want to make sure I get the content through first. Okay, I'll try to revisit that at the end. Apologize, hopefully it's okay. And then now the last bit to relate, remember that for triangle, not a triangle, square between U delta U V delta V, right? So now I've explained what is the relationship between these, and then now I've explained U and V, right? So what's left is delta U and delta V, but it's exactly the same thing. So I'll just squeeze it in here because it's very simple. So the relationship between delta V and delta U, right, is just divide by Q. Write that. So just again to remember, this is from A to B. If we're talking about energy, right? A to B, FDR. From A to B, this is A to B, FDR, but V always have per unit test charge. Okay, so you combine this, it's clear that this is the relationship. Or you can just think of putting a delta on both sides over here. Okay, so same thing. You can rewrite it like this. So you can just think of putting a delta here. The test doesn't change. The test charge doesn't change. Okay, I'll try to slow down a little bit. Thank you for the feedback. Yeah, so you can think of it like that and achieve this equation. Okay. Does that make sense? So now we have the tie of all four of these things tied together. Okay, so energy, one more time, is energy and potential. The relationship is the potential is this divided by test charge. Okay. Maybe I'll erase that. Okay. All right. See how we're doing. Okay, good. Now, since we just mentioned this, let's actually make this even more explicit. How do I actually relate the force approach to the energy approach? So I'm going to expand my square a little bit, and as I've already told you that U seems to be related to F, and E, because it's force per unit charge, seems to behave like the V, which is energy per unit charge, right? So let's actually draw this final link together as well. So this is the relationship between force and energy, force and field versus U and V. Okay. So this is the force side of the approach. This is the energy perspective of things, right? So one side we have this relationship. So V is U over Q essentially. So now let me not write the word test, and just to keep things simple, right? So this is E is the new thing, right? It's force per unit charge like this, okay? So let's look at the actual definition. How do I go from U to F? How do I actually go from there? Well, we already talked about, let's start with one dimension. At Ux, at a point X, is from a reference point X naught to X. Okay, so this time I don't, looking just purely at the X component of things. So it's the same thing I wrote before, right? From a reference point to a certain location. But now let's just look at the X direction, just purely in one dimension first. And I can reverse this, because if one is the integral of another, then the other must be a derivative of the other, right? So this is another way you can relate the two. So this part, again, as I already said in the beginning, it's going to be a little bit more mathematical, but after I fill in these two blanks over here, in the next slide, I'll give you a concrete example, and hopefully things will be more clear. Now, in larger than one dimension, you have to be, it is a little bit more mathematically complex. So you might need to do a little bit more reading on this part. In the lectures, I'm not going to, as I mentioned many times, I'm not going to give you every excruciating detail, but I'm going to tell you what you want to read up on and what you need to know. So unfortunately, this is the part where I will not have time to explain all the mathematics behind it. Okay, so now let's go to 3 dimensions. So I'm going to change the X into R, okay? In fact, let's make everything clear. It's a 3-dimensional vector from a reference point to the location of f dot dr, like that. Now, how does dot products work? Well, dot product, right, so maybe I should write this. The f vector means it has components. It means you have the x component, y component, and the z component, like this. Okay. So what a dot product means is you take this, I'll temporarily write it over here. So dr is just, so r is x, y, z. Some of you might be wondering, you can write it like this as well. I like to write it in a column because it is easier to write. I don't have to write too much redundant things because they're the same way to think about. If you're more comfortable with this, that's fine. I like to just put everything in a column, then it saves me a lot of writing, right? So what about dr? Remember, don't think of d as like a derivative. Think of it as a small change. Okay? It is a derivative, but it doesn't help you in any way if you think of it as the mathematical sense of all those different rules of how to do a derivative, pull down a power and all those things. That's not going to help your life. What's going to help your life is understand what does a derivative mean, and what it means is a small change. Okay, so think of it as small change. Then if you have a small change in a three-dimensional, if you move in a three-dimensional step, then that means in each of the direction you move a little bit, right? So you just put a d in every part. That's basically what dr is. And then how do you do dot products? Okay, just a recap is if you have fx, fy, fz dot dx, dy, dz. So this is f dot dr, right? What you do is you multiply these together and add up all the pairs. So it's multiply this plus multiplies this and this plus multiply the last row like that. Okay, so let me fill in the blank over here, r naught to r. We have fx dx plus fy dy. Everything is a scalar now. Okay, so if you are foreign to this, if you don't know this, you might want to spend 15 minutes to do some YouTubing and excuse me, on how to do dot products. Okay, so go and it won't take you more than 10-15 minutes to find a good video to understand that. Okay, right. Okay, so what that means is, remember fx is du dx. So can you guess what fy would be? It would be du dy, and fz would be du dz. Okay, again, this is not a math course, so unfortunately, as much as I want to slow down and oops, sorry. Am I still here? Just checking. Okay, good, sorry. Thank you. Yeah, so as much as I want to actually slow down and go through the math, I mean, it's very interesting mathematics. It'll take me a 20 minutes detour to talk about math, since this is not a math course. I'll just state the result, and you can go and do a little bit of research on yourself to understand it more if you will. So here is going to be du dx, du dy, and du dz. But before you copy this part, we actually don't write the normal d, we write what's called a partial d. Okay, so it's going to look like this. That just means ignoring, when you do a differentiation with respect to y, ignore everything else. So this is called partial derivative. It's just like a normal derivative, but when you're doing the derivative with respect to x, then you just treat everything else as a constant. Okay. Again, another thing you might want to read up is partial derivative. If you know that well, that's fine. If you don't, again, it's just a normal derivative, but you treat everything else constant. You can, in a 5-minute YouTube video, you'll understand what to do. Just find examples of this online. Okay. All right, so this is the relationship between you. So I'm going to put a box around this. Maybe I will put this in the next slide. I want to put something else side by side. Is between V and E. So remember, V was, what was V? So V was, I'll ignore some of the signs like this, right? Q test, ignore some of the limits. And we talked about yesterday that this is basically the electric field, right? So you can rewrite it like this. So let's use that to write it as x naught to x, E dot dx, sorry, no, this is just one dimension. Then this is the same thing as Ex is dv dx. So I want you to parallel this with the left-hand side with F and U. So you see it's the same idea. So I don't have to explain too much. It's the second part. If you have more than one dimension, you can fill in the blanks, right? So this would mean it's the same thing as if E is dv dx, dv dy, it's the partial d is still pronounced d. So this pronunciation wise, it's nothing different, right? So ex is equals to that, ey, the y component is equals to that, and the z component is equal to that. So this is the relationship between v and e. One is the derivative of the other, one is the integral of the other. Okay, so if you integrate e, you get v. If you differentiate v, you get e. But e has components, so you need to differentiate with respect to which coordinates you get that component of that coordinate. Okay, so this is what this is the takeaway from here. One more thing to introduce, not a new takeaway, but just a new symbol, a new jargon is you see mathematicians are very lazy. They're very lazy animals, and they invent new symbols whenever they have to write more than 2 strokes. So you see, I keep writing ddx, ddy, ddz. It's very redundant like this. So they invent a new symbol for it, which is an upside down triangle. Okay, so an upside down triangle. So they can write E as this times V, like this. So what is the upside down triangle? The name is called a nabla or del sometimes. So del V means, so the nabla means ddx, ddy, ddz, right? So when you do this, then the V just goes, the V just goes inside, and you can have this result over there. So you'll see this nabla come up. So unfortunately, I hate doing things without explaining the reason, but unfortunately I have to do it, is there's an extra minus sign here, which is not easy to explain without the full half a mathematics course like that, but there is a minus sign in here. So for now, I'll just quote it without proof. So for here, the relationship, there is a minus sign between all of these. Okay, so this is one of the point where there is a reason for it, but due to the time, I will not be able to sufficiently explain why there is a minus sign. All right. The key is how to use this knowledge, this new knowledge, and I'll show you in the next slide in an example. So let's say I have a plane charge like this. Okay. So when I have a plane charge, I'm just drawing the cross section of it. So let's say this has plus sigma, right? Remember, sigma is charge per unit area. So there's a lot of positive charge on here on this plane. Let's say it's an infinite plane. So how does the electric field lines look? The electric field lines look like this. Right? This side points this way, this side points this way. So now you should be an expert in how electric field lines look. And let's pick a few points. Let's call this point A and point B and point C here. Okay. So here's my question. Okay, so can you find a potential difference between A and B, between A and C, and what's the last one? B and C. Okay. All right, so I'll work this through with you. Let's say this is 8 meters apart, and let's say this is 4 meters apart, like this. Okay. So the first step you want to do is always start with a definition. Okay. So step 1, recall the definition. So the definition of delta VAB, just write it out, right, is from A to B of E dot dr. Well, technically F over Q test, but F over Q test is the electric field. This is the more practical version, especially if we know the electric field of this. Yeah, just a recall if you forgot. For a plane, the formula is 2 epsilon naught. Right? Do you remember that? Right? So for a plane, at any point, at any point in the here, it doesn't depend on the distance away. So it's actually a constant. The whole thing is a constant. It makes things easier. You won't get something too difficult in the exam. So this is a good example. All right. Also, my points are in more than one dimension. So I do need the more than one dimension version of this. Okay, so since it's more than one dimension, I need to use this version of it. So next, plug in, find out what E and dr is. Well, dr we already know, it's dx, dy, dz. What is E? Let's properly write that down, the E vector. So find the E vector and dr vector. Okay. So let's look at the direction first. The direction of E, the electric field, as far as I'm concerned, between A and B is pointing to the right. So let's use the standard where this is positive X, this is positive Y, right? Positive Z, let's say it's going out of the page, out of the screen. So the direction of E is just in the X directions, or in my notation, it has an X component, but no Y and Z component over here. Can you see I'm interested in the electric field between, so I'm interested in the electric field between, it's the E between A and B, and a small movement, this is a small displacement, right? Small change in distance from A to B. So it's E between A and B, and this displacement between A and B, but that's a small displacement. Okay. So I only have the X component over here. If I need to draw a free body diagram here, right? So the electric field is pointing this way. So E vector only has X component, whether it's at B, at C, or at A. Okay. So that's why I can write it like this. Immediately make the other two. There's no Y component and no Z component. Now dr is, as we said, dy, dx, it's a small change in every possible direction. And then also, so what is Ex? Well, let's have the magnitude. Just so remember the magnitude of this, which is just the magnitude of Ex in this case only, right? And now you use the formula of a plate. Of a plane is sigma over 2 epsilon. Okay, so we know that Ex is sigma over 2 epsilon because that's the magnitude of it. Okay. So this goes in here. Okay. Well, so if you like, you can put everything together and you can write E is, but this is too much writing for now. If you like, you can put everything like this, but for now, we'll just work with Ex, and at the end, we'll just plug this in. And then now you just plug it in the definition, so, and solve. So plug in the definition. All right, so delta VAB, here's the math part. You go from A to B, and it's Ex 00 dot dx dy dz. Right. With what I taught you, how to do dot products is just multiply the top row plus multiply the next row, which is 0 times dy, multiply the next row, which is 0 times dz, and add them all together. So clearly this disappears. And you're left with integrate AB. In fact, let's pull out Ex because it's a constant, as we mentioned. Gonna save a few steps. Dx. And what is integrate dx? Well, it's just x from A to B. And now you plug things in. It's xb minus xa. Okay. And so this is actually, you can see this is actually delta x, but we'll keep it that way. And now so yeah, so what is xb minus xa? So which side is x? This side is the x coordinate, right? So the x value of b, let's call this the origin. Let's say this is x equals 0. The x of b minus the x of a, what will it be? So this is just the difference between here. So it's 8 meters. Okay, so so this is 8, right? So you just plug that in and you get sigma over 2 epsilon times 8. And that's your answer. Okay, you can simplify this for sigma over epsilon like this. In a real homework, probably you'll be given what is the sigma, or you'll be given the charge and the area, right? You'll be tell how much charge there, how much area. So you will plug this in, and then you look up this value. You plug this in, you actually get a value out of that. In terms of the SI units, is volts. Right? So you'll get a whatever the number of volts is, like that. Okay. All right. How do you do from A to C? Do I have time to do that? Yeah, I should do that as well. Yeah. Okay, so from A to C, let's do it with a new diagram. So let's repeat the process. Hopefully this time it will be quicker. So from A to C, this time I would write AC E dr, right? And the electric field is already, it's purely in the x direction, right? Even between A and C, look at the electric field, it's always pointing in the x direction. And dx is the same thing, like this, right? So now we will write this out. So we have AC EX dx plus a bunch of zeros, and you multiply those out. And then now you integrate this, you get xc minus xa, right? From A to C. What is xc? What's the x value of c? Whatever that is, it's the same x value as a, right? Remember, this is x, this is y, right? They have different y values. So that's, I can put a coordinate like this, y. But you see, xa is this, the x value of a and the x value of c is the same. So this is actually 0. Okay, so the whole thing is 0. What does that mean? That means the potential difference between this point and this point is 0. That means they are the same potential. Okay, so therefore we find that VA is equals to VC. The absolute potential is the same. Since the difference is 0, there's no difference. Okay, so this is actually an important conclusion. Okay, that we find that this is the same potential. You can repeat a process by putting a point D over here and show that B and D is also the same. So every line perpendicular to the field has the exact same potential. Okay. Yeah, so what this leads to is the idea of equipotential surfaces. Okay, so just what I mentioned in the beginning, we try to find a way to visualize the potential, and now we have one just by doing this. What we find, maybe I'll use gray, is over here on this line. Actually, it's a surface because this guy has there's a depth to it, right? It's a plane of charge. So there's actually a whole plane over here that has the same potential. So everything on this line or on this surface is the same potential. And this is called the equipotential surface. Okay, does that make sense? In fact, so you can find a point D over there and try to do the same math, and you can see that that has the same potential as well. So these are equipotential surfaces on these. But is this the same potential as this one? No. Okay, so here, let's call it VA, VB. So VA does not equals to VB, as we just saw from previous slide, right? There is a potential difference between A and B. It's for, I think, whatever that number was that we calculated. If it's 8 meters apart, it's like that. But on this line, on this surface, the potentials are the same. Okay, so I can generalize this idea, and basically every straight line like this will have the same potential. Okay, it's getting a little bit cluttered. Let me redraw this to make it clear. So this is a charge, and these will be the equipotential surfaces. So that's the white one is the source. It's the plate where is a plate of positive charge. So this guy has some positive surface density, right? So Q per unit, charge per unit area, if you remember. And all of these are called equipotential surfaces. So maybe this is VA, VB, let me use a different notation. This V1, V2, V3, V4, right? Yeah, either way, you can, each one has a different potential, but on that line it's the same. Let's overlap it with the field lines. So these are the field lines. So here you can see one takeaway is that the equipotential surfaces will always intersect the field lines perpendicularly. Okay, so takeaway one is the equipotential surfaces will intersect with 90 degrees with field lines. I can show you a better picture. So, also we often use dotted lines to show the equipotential surfaces. So you see the red ones are the field lines. This one actually have two plates. I have a positive and a negative plate. So it's going from the positive to negative. These are the field lines. Let's just zoom in over here. And then the green ones, the dotted lines, are the equipotential surfaces. So here there's the same potential like that. There is some edge effects if you want to include that. So you see this bends a little bit. So we just learned that they should interact perpendicularly, right, with 90 degrees. So you see if this one bends like this one bends further like that. Okay. So with what we learned here, we can actually look at how about for a point charge, because we are usually more interested in a point charge. Well, how does the field line look for a point charge? The field line looks like this. And how would the equipotential line look? Well, it has to intersect with them 90 degrees, so it must go like this. So these would be the equipotential lines. So remember the first slide I sketched? Those are how the equipotential lines look like. Okay. So it could be that, this is 100 volts, this is 90 volts, this is 80 volts, this is 70 volts, like that. But along that circle, technically it should be a sphere, it should be a surface, right? Because it's surrounding it. The field lines go out in all directions as well. So the sphere, the potential surfaces should wrap around in all directions as well, like that. Okay. Another way to be able to tell this is, remember the potential for a point source is KQ of the source over R, right? So you can immediately see that if you have the same R, you will have the same V, right? This source is constant, and if you have the same R, you have the same V. So along here, you have the same R. So you have the same radius, the potential will be the same. How do I know the potential starts decreasing as I go further and further out? Well, let's look over here. Another thing is, if you see that as the R increases, V decreases. Okay, so here is takeaway 2 for point charges or point sources, let's say. Number 1, the equipotential lines are spheres, circles and spheres. Number 2, it decreases as it goes. So if I plot this graph like this with R and V, you see that it's basically like a 1 over R situation, like this, right? So at a certain distance, very close, at a very close radius, you might have 100 volts. I'm just making up these numbers. So, but technically, if you plug this in, right, you plug this in, you'll actually get the number. But now I'll just write this out, right? So the further away you go, the potential will decrease. If you go all the way to infinity, what is the potential? 0, right? So if you go all the way to infinity, the potential would be 0 volts, like that. Right? The closer you go, the higher the volt. You can't actually sit on top of it, otherwise it'll blow up to infinity. But yeah, okay. So now this leads us to takeaway number 3, is how do positive charges move? Because remember, our ultimate goal is to understand how do things move. So in the field line picture, it goes from, it follows the positive charges would follow the direction of the field lines, right? Now we have a new takeaway, is that in the potential picture, even if I don't tell you anything about the field lines, and I just tell you the potential, you will be able to tell how a positive charge moves. Okay, the takeaway is it always moves from high potential to low potential. So positive charges always move from, I'm not going to write in full sentence, from high V, high potential, to low potential. Okay. So this is the potential perspective. You can have the field perspective where positive charges would go along the field lines, right? It will move along the field lines. So you can think of it in terms of the potential picture or the field lines picture. So even if I erase the field lines and now ask you, if I put a positive charge here, like this, I can ask you which way will it go? And even without the field lines, you can tell me it will not go up this way, it will go down this way, like this. So without the field lines, I can also, just by looking at the equipotential surfaces, so that's a way to visualize it. Okay. Oops. I apologize, I'll have to overrun for 10 minutes more. So I'll expect around 8:40 that will end today. Okay. Yeah. Okay, so yeah, so I can show you another picture here. This is just basically what I drawn, just to give you a more computer graphic generated version. You see the field lines, you see the equipotential lines around it from high potential to low potential. How do they actually get this value? You just plug in the, right? So it depends on the distance away from it and the source charge. I can't tell you without knowing what the actual point source charge is, or how far away is this, 1 meter, or is this 2 meters, or is this 0.5 meters? You know, I need the actual distance away. You plug in those numbers, it will give you in SI units, whatever that is. Okay. All right. So I'm not going to draw this out, but you can see if I have a dipole, remember, di means 2, pole means 2 charges. These are the field lines, and the surfaces are intersecting with 90 degrees. And these potential will go from high potential to low potential as well if you actually calculate in the number. This time you'll need to actually add up the 2 potentials. So at this point, if you want to know, say, the potential here, you first calculate the potential due to this guy plus the potential due to this guy. So V at any point, will be the potential due to the positive one plus the potential due to the negative one. Now, these are scalars, and it's very, very, very easy to add. You do not need to resolve vectors at all, right? So that's the beauty of potential. Okay. So another way to think about potentials is actually, how many of you know what contour lines are? If you go hiking, you probably will know this. How many of you are familiar with this? So you can think of equipotential surface like contour lines. Instead of thinking of high potential, think of it as high elevation to low elevation, right? So you can think of a positive charge creating a high elevation, and any negative charges, negative sources would create a low elevation. So these are basically equigravitational potential lines, because if you hike around a equipotential line like this, your height doesn't change. Around this line, if you keep hiking around this line, so if you want to claim that you went hiking, but you want to be lazy, just walk around this line and you do very little work. In fact, you do no work. You do zero work against gravity. You just do work against friction. So you're doing work against the horizontal force of friction, but you don't do any work against gravity, right? So that, sure, you have to do work to move yourself forward, because in this world we have friction, as we learn from thermodynamics. Every time you step on the ground, it heats up a little bit, and that causes entropy to increase. So you have to do work against that friction, but not against gravity. Okay, so here is the same. This positive charge, if I move the positive charge around the equipotential surface, I don't do any work against the electric force. It will be free of charge. Yeah, no pun intended, free of charge to move around this side. If I move against it, it's like moving a mass uphill, right? I will need to cause me some work to do it that way. Now, if it goes downwards, I also don't need to do any work. The electric field is going to do the work on the charge. So the electric field, or the potential, is going to cause it to move this way on its own, right? So it's going to go from a high potential energy to a low potential energy, and that is going to, it's almost like an apple falling from high gravitational potential energy to low gravitational potential energy, and that will change into the kinetic energy, right? The apple will go faster and faster as it rolls down the hill like this, okay? And this brings us to takeaway number 4, the last key takeaway over here before I talk about a few applications so probably 2 more key slides over here, is that only potential difference matter. Okay, I'll write it in the new slide. Only delta V's, the delta, matter. The absolute potential doesn't really matter. So sometimes we say only the difference, only potential difference, only delta V affects the physics of things. Physics basically mean how things move. So only if you think of an apple falling down in the gravitational potential, you can call this y equals 0 and this y equals to h. In that case, your GPE at first, it's going to be mgh, and your kinetic energy on top is going to be 0. Let's say you start off 0, and at the bottom, so GPE initial, kinetic energy initial, GPE final is 0, right? Because GPE is mgy. Gravitational potential energy is mgy, so at the bottom is 0. And what is the final kinetic energy? Well, you need to now know that the change in all the potential energy plus change in kinetic energy is 0 because of conservation of energy. So KE is negative of the gravitational potential energy. So final minus initial, which gives me mgh, right? So if this is half mv squared minus 0, because change, then I can find, okay, the m cancels, so I have v squared equals to 2gh, and I can find the v is square root of 2gh, this, right? So that's one way, but I can equally call this 0, and this is minus h, like this, right? So the distance is h, but I can redefine this as 0, and this is minus h. So the absolute GPE here, so the GPE here is mgy, right? It's going to be 0, and so the initial, and the GPE final is going to be mg minus h, right? So minus mgh. What is the change in GPE? So final minus initial, so final minus initial, which is mgh, minus mgh, right? Did I do something wrong? Maybe I have to actually do it properly for this to work, for the signs to work out. For now, the sign, yeah, so if I do it properly, there's a constant to work. So let me do the cheating way, where I'll look at the magnitude of things and work out the sign later on. So the magnitude is mgh, so that's how much GPE is lost. So any lost in GPE will be gain in kinetic energy, right? So the kinetic energy will gain this amount, and it's the same over here. You see the kinetic energy has gained this amount. So the actual whatever you call the actual potential does not matter. It won't affect the speed. The only thing that affects the speed is the difference over here. Okay, so actually in 3A you may actually see this GPE written this way, right? It's only the change in y that matters. It's only the delta y. It's the change in, so that's basically y2 minus y1. This is the absolute potential at 0.1, absolute potential energy at 0.1, absolute potential, sorry, 0.2, absolute potential energy at 0.1, but it's the difference that affects kinetic energy. Okay? And yeah, so now we can tie everything together is why things move. So one reason is it moves because the electric field exerts a force. And the second reason is a difference in potential causes a difference in potential energy, which causes a difference in kinetic energy. Okay? And this causes acceleration. So this is the force perspective. This is the energy perspective of why things move. Answered. Okay, makes sense? All right, so this way you calculate the field lines. It is a vector, which is maybe not everyone's favorite, but it's very easy to visualize. The field lines tells you the force. The field line tells you the direction of the force. Coulomb's law will tell you or all those formulas I give you will tell you the magnitude of that force. You can calculate the acceleration. Or if you like scalars better, then you just add up all the potential, which is much more abstract, which I agree, very, very abstract. But the math is much more easier because now you just look at the difference. If it goes from 100 volts to 90 volts, right? So the difference is 10 volts. You multiply by the charge, you exactly know how many joules of potential energy. Let's say the charge is 3 coulombs. So the change in potential energy is 3 times 10. So it's 30 joules. So you will gain, if you lose 30 joules of potential energy, you will gain 30 joules of kinetic energy, right? Does that make sense? Okay, cool. Lastly, I'll just list the applications. Might take me 2 more minutes. Is you can build an electron gun out of it. At first, you might say, "Who cares about electron guns?" But it's quite cool because you can first take a piece of metal, you heat it up. And now it will start emitting electrons. The electrons in the atoms would jiggle a lot, and they'll start emitting in all directions. Where you burn it, and they will gain a lot of heat energy, a lot of vibrational kinetic energy. At some point, that it vibrates out. Now you can put a positively charged plate here with a hole, because a positive charged plate will have electric field, right? The electric field going this way. Now the negative charges, remember, they go against the electric field because positive charges go along the electric field. Negative charges would go this way. So you will actually get the electron to accelerate all the way through here. And on the other side, you might need to put a negative plate so it repels the electron further out like this. So the field lines would go like this, right? So the field line goes from positive to negative like this, but once the electron goes past here, the electron will keep getting repelled from the negative plate and will shoot out. So this is what an electron gun is. It is very significant because this is the device which actually proves that atoms exist. If you've heard of Rutherford's experiment of what is that called? Splitting the atom. What he did was he took one of these guns and he shoot it. So he took one of these guns and put positive and negative plates here, heat it up over here. Now it starts emitting electrons. He actually used a different type of particle called alpha particle, but doesn't matter, the theory is the same. You shoot out these charged particles against a gold foil. Normally, it's so high energy that you can shoot these electrons that you'll expect that it will just pass right through, unless there's something very hard over here that it hits on and bounce back, and that is exactly what happens. So the electrons hit on something that bounce back. So the old model of an atom is called the plum pudding model. Plum pudding. They thought the atom is just made of positive and negative charges like a pudding. But now, when he takes this gun and shoot at it, something bounced back. Then he realized that probably there's something very hardcore in the middle, which he calls the nucleus. And the electrons, which is positive, and the electrons are on the outskirt like this because the electrons are easier to get emitted out, right? So when for a lot of electrons, they pass straight through, but every 1,000 electrons, there's one that bounce back because there's a chance where it hits the nucleus and bounce back. All right. So in science, this is one nice application. But this, you might not care about this, but you might care about a television because it is the same idea how they create, not the new modern flat screen TVs, by the way, it's the old fashioned ones. That you see the cathode over here is there's a heating element. It's heating out all the electron. It shoots out like an electron gun. This part where it calls the anode is where the plates that I just drew, the electrons will shoot through here. Now they put in two additional ingredients. One is they set up two parallel plates with different charges, and it will be able to deflect the electron left and right. Here, it will be able to deflect the electron up and down. So what that happens is it will shoot out to a screen. The electron, this is going to be like a film, the old, if anyone still remember the previous generation, people use film to take pictures. So when things hit the film, it will create a bright spot. When the electron hit the film, it will create a bright spot on the fluorescent screen, right? So this is why you see old televisions, there's this huge thickness behind it. It's basically this electron gun shooting electrons on the screen, and the two plates control the horizontal movement to shoot the electrons where it wants to be bright and where it doesn't brightness. Color is a whole different thing, by the way. This is a black and white television. So it creates parts where it's bright and parts where it's dark. And the plates will control it so that it goes first scan through horizontal and then in very rapid successions like this, and control the electrons to show whether if it wants this part to be bright, it will shoot an electron here, and if it wants this part to be dark, it will just stop shooting, and then the next part to be bright, it will start shooting again. And this is why you will not only see that the old school televisions have this, and you will also see a lot of lines. If you take a film of it, you can actually slow it down slow motion. You see all these lines like this. These are electrons hitting this screen. Okay. And finally, the last thing I mentioned is it's the birth of a battery. You can use this theory to create a battery. What is a battery is basically you put one side, it's a positive plate, one side is a negative plate, and you connect it with a wire. If you connect it with a wire, now all the electrons would go from the negative side to the positive side. So you set up an electric field, or as we like to call it, an electric potential difference. Over here. So you set up a potential difference, and it will go, positive charge will go from high potential to low potential, and negative charge will go from low potential to high potential. So that's why you hear batteries are 9-volt batteries, 1.5-volt batteries. All these are telling you the potential difference between two sides of that battery. And this is the key thing that kicks off the whole modern electrical revolution of our world, because once we have batteries, we can actually make circuits and all the electronic devices we have in our everyday life. Okay, all right. Sorry, ended even 5 more minutes later than I told you, but that's it. Thank you very much. Any questions? I'll stay for a few seconds for any questions, but otherwise you're free to go. Okay, you're welcome. Thanks for staying. Thank you. Okay, I think we're good. All right. Have a good night. Bye.